right? You are all set, correct?
Yes.
Okay, okay. Because I got my team viewer up. Now I'm connecting to the meeting, see whether I can be able to see.
Are you on?
Yes, I'm here.
How is my voice? Is it clear?
It's very clear.
Okay. So are we ready to start?
Yeah.
Shall I go ahead and start?
Yes, please.
Okay. Ni hao. Ni hao ma.
你好。
大家小安。谢谢你。邀请我。The topic for today is words of wisdom from an 80-year-old petroleum geologist to a 4-year-old Energy Geoscience journal. I'll mainly talk about deep water deposition, but I will also cover some of the other topics that are of relevance and timely. These are the topics I'm going to cover. There are 26 topics. I have to go through these 26 topics in order to reach the final one, that is the words of wisdom, so that you'll know how I arrive at this words of wisdom for today. To give you some background, I was born in a small town called Sirgari in southeastern India, British India. I was born in 1944. Today it's called Tamil Nadu. And I received my bachelor degree in geology and chemistry from Annamalai University. Then I got a job as a science teacher in a local high school. That should have been the end of my professional career. But the head of the Department of Geology, one by name Professor T.N. Muthuswamy Iyer, called me into his office and told me in no uncertain terms that I must resign my job and go to Bombay and study my MSc in Applied Geology at IIT Bombay. IIT stands for Indian Institute of Technology, one of the top schools in India for science and technology. I told him there is no way I can do it because I'm from a poor family and so on. But he said, get some loan, go and study, otherwise you'll be wasting your life. So I took his advice, went to IIT Bombay. I was the top student in applied geology. They gave me a medal. Then I went to America. Professor Parthasarathi was my advisor at IIT Bombay. He received his degrees from Imperial College, London. In Ohio University, I studied under Dr. Fisher, he received his PhD from Cornell University. Then I studied my PhD under Kenneth Walker. He received his PhD from Yale University. My PhD thesis is on the Southern Appalachians. It's a very complicated topic. I published several papers that landed me a job at Mobil Research in Dallas. And Mobil was the second largest oil company at the time. From this building, I studied rocks in Australia, New Zealand, Alaska, and so on. As I said, Mobil was the second largest company in 1978. So they wanted to expand the research. They put a lot of money into it. And then they wanted to build a new building. So they hired I.M. Pei. He was the top architect at the time from China. He got his degree from MIT. He was the one who designed the Louvre Pyramid in Paris, France. And he was also the one who designed the Bank of China in Hong Kong. So if you go to these cities, take a look at these buildings, some of the most beautiful buildings you could see. He was the one who designed this research laboratory for Mobil. This is where I spend most of my time, studying the Washita Mountains, North Sea, Norwegian Sea, Nigeria, China. Then I moved to this building. From there, I studied Gulf of Mexico, France, Ecuador, Gabon, Brazil, and so on. Then I retired in 2000, started teaching in Texas, University of Texas, and so on. And I started publishing. I have published 5 books, all by Elsevier Publishing. 2 of them have been translated into Chinese. I have over 380 published works. As a result, I received this Professional Achievement Award from Dr. Lee. She's the Dean of College of Science and Arts and Sciences at the University of Tennessee. Then I serve on these 3 journals today in the editorial board. For example, I am the Associate Editor-in-Chief of Journal of Paleogeography. I'll be giving some information more on this today. I also consult with various oil companies, including PetroChina, Reliance, ONGC, and so on. I have conducted workshops all over the world, 15 of them to date, in these countries, Brazil, India, China, and so on. I have given 92 lectures internationally. 92, today is the 92nd of this one for Energy Geoscience. I have participated in the AAPG debate in Dallas in 1997. This is all for knowledge transfer. This is an example of photograph, the core workshop I did for Reliance in India. This is for RIPED in China. This is Dr. Kaineng Zhu. He was the head of research at the time. This is in Qingdao, where I conducted a workshop. So early this year, March, I was reading World Oil. And it said the China National Offshore Oil Company Corporation made a major deep water oil and gas discovery. So this got my attention. I read the article. They said the water depth, the drilling depth, was 500 meters. Yes, that is deep water. Usually we consider more than 200 meters deep water. So there is a problem with the word deep water. What is deep water? Depending upon whether you talk to an engineer or whether you talk to a geologist, they have a different meaning. For example, this is well A. If you talk to an engineer, he would say that this is a shallow water well because they're talking about the drilling depth. But if you talk to a geologist, he'll be talking about the depositional origin of the bed that this one is reaching for. This is a deep water. So he will say this is a deep water depositional system. If you go to the well B, the engineer will say this is a deep water well. But if you go to the geologist, he will say it's a shallow water origin. So we have to be very clear. When we say deep water, are we talking about the engineering aspect, that is the drilling depth, or the geologic aspect, or the depositional depth? The other issue I would like to set some clarity to the scientific stages of development. I used the model by Thomas Kuhn. He said normal science normally start with first random observations. Then we go to the first paradigm stage. Then there are a lot of confusion and crises, complications, the big question mark. Then we fix the problem, that is the revolution stage. Then the normal science thrives and flourishes. So that's the 5 stages of scientific development. As far as the deep water deposition is concerned, we went through the stage 1 and 2. We are in the crisis mode. There are a lot of confusion, complications. That's what I'm going to talk about today. Before we do that, first, I'd like to talk about fan deltas and bright deltas. In the year 1987, McPherson, myself, and Mayola published this paper in the GSA Bulletin. Before that year, any coarse-grained deltas, like an alluvial fund going into a standing body of water, we call it fan delta. Even if there is a brighter channel in front of it, we lumped all this together, called it fan delta. That's wrong, because this brighter channels, this alluvial fan, are 2 different depositional systems. This is deposited mainly by debris flows, therefore poor reservoir quality. This is deposited by brighter channels, a lot of reworking, high porosity and permeability. Therefore, we should distinguish this from this. This is a modern example of a fan delta. This is a modern example of a bright delta. The next example I'm going to talk about is the Gippsland Basin in the southeastern Australia. The orthodoxy is Kumi coal cannot generate oil. You need marine organic matter. So if you look at this basin, it has got 3 billion barrels of oil, but there is no marine organic matter to provide the oil. So where the oil comes from? That's where I had started the study in the early 80s. I went to Australia, studied these coal beds, and I found out there are a lot of resin balls in these coal beds. They come from a unique tree called kauri tree. And this tree grow today in northern part of New Zealand. So I went to New Zealand, studied these trees, collected the leaves and the other materials. These are the leaves we got. And when you look at that under the scanning microscope, you have this waxy coating. These are the waxy material that provide the alkanes for the oil. So we have resin, we have the waxy coatings, and so on. So we can also test where the oil comes from. You take the actual oil, that's the green dot, and you take the coal extracts from the samples, and you plot them in the pristine phytane plot. All of them fall in the terrestrial material zone. None of them comes from the marine source. So you can easily say the oil come from the coaly material or terrestrial material. So I published this model in the AAPG Bulletin in 1985. That's 40 years ago. If you go to Google Scholar or ResearchGate, this paper is one of the most cited papers of all my publications after 40 years. So this is an example, good science stands the test of time. Then we go to Alaska. The orthodoxy is the porosity is primary, that is the depositional porosity. But if you go to this one of the largest oil field in North America, called the Prudhoe Bay Field, when you look at the core, before we look at the core, I want to show the stratigraphic section. This is the reservoir, Permo-Triassic reservoir, that's being truncated by a major unconformity. This is the oil field. So you take core from there, and this is how the core look like. You have the black grains, that's fresh chert, microcrystalline silica, and it forms little rim due to weathering, second stage. Then it goes to complete white grain, that's the third stage of alteration. This is under the microscope. This is the rim. If you didn't see the previous example, this is a petrographic photograph, thin section photograph. So that's the second stage. The fourth stage, the grain got completely dissolved. This is also under the microscope. This is the grain before dissolution. This is the grain, complete dissolution. It's all gone. It's just a hole there. So I provided this four-stage dissolution. Pre-dissolution black chert, weathering rim, complete alteration white chert, and complete dissolution. The chert is completely gone. All right. So why this happens? Then you have to study the paleoclimate. At the time of the unconformity in Alaska, the paleoclimate is very much like what it is today in Guilin in southern China. So if you go to Guilin, what do you see? These large tower karst. Of course, these are all limestones. I'm talking about silica. And if you go to the Guilin River trip, you'll see these large caves. So you can think of as a large porosity. There is a man standing here inside the porosity. As I said, these are silicate grains. So how we dissolve them? When you do the petrographic analysis, you see these little needles. These are all apatite crystals. When you look at the composition, it's got fluorine. The importance of that is it increases the solubility of silica. So I generated this model. We have dead animals, bones, and they generate fluorine and so on. We have a lot of rain like southern China, and it goes into the rock, into the reservoir, cause the dissolution of silicate minerals. That's what I came up with my colleague Higgins. We published this paper in the AAPG Bulletin in 1988. And we also plotted. This is the Prudhoe Bay Field. This is the cross-section we are looking at. As you plot the porosity, measured porosity, that's mainly secondary porosity due to dissolution, it increases as you come to the unconformity. So the porosity increased towards the unconformity. So we have petrographic evidence, geochemical evidence, paleoclimatic evidence. This is also one of the most cited articles in the last 30 years or so. Then now we are going into the deep water, kinda. This is called hyperpycnal flows. I published a paper on this in the Journal of Paleogeography with a big question mark, because these are flows that comes from rivers, cross the plunge point, and moves into the shallow water. But these are very feeble, low-key flows. They die out immediately. But there are authors who believe that it goes all the way to the shelf edge, come down to the deep sea, forming submarine fans and so on. There is no evidence for it. Nobody has documented that these flows go all the way here. Until they document, I won't believe it. There is the other complications. There are 16 types of hyperpycnal flows. So when you read a paper on hyperpycnal flows, the author doesn't identify which one of these 16 types he's talking about. So that's another problem. And when you go around the world, look at the hyperpycnic flows. This is Yellow River in China. Depending upon which year you are looking at, the shape changes. This is the Mississippi fan. So I surveyed all the plumes around the world, and I come up with this summary diagram. And this is also published in one of the journals. I also published in PED, that's Petroleum Exploration and Development. This is one of the areas we need to pay more attention. Very few people study these plumes, so that's another area of future research. Let's take the Elba River in the US. This is the river comes in. Normally what happens when it exits the river mouth, you form a delta, or you go into the deep water. This is the Strait of Juan de Fuca. In this case, the sediment take a 90-degree turn. Why? Because of the wind forcing. This is a very unusual situation. But we need to understand, if you want to understand source to sink, normally we think the sediment comes from here, goes down to the sink. It is not always the case. In this case, takes a turn, go this way. So we need to understand this. Therefore, there is another question mark, area future studies. These are the papers I have published, but there are very few other examples of this kind. Now we actually go into the deep water, that is the shelf edge. The major processes that occur here are slide, slump, debris flow, and turbidity current. But in the last 60 years, we spend more time on turbidity currents and very little time on slide, slump, and debris flow. There are people who worked on this, but not to the extent as we spend time on turbidity currents. The reason I put them in yellow and this one in blue, because these are more important sandwich systems than this one. So we literally wasted our time studying turbidity currents instead of focusing on these deposits. Let me give you an example of what I'm talking about. When you go to London, take a look at this double-decker bus. Can carry 73 people at a time. That's very similar to mass transport, debris flows, and things like that. But if you go to Scandinavia, they have this micro car that can carry only 2 people. That's like turbidity current. So which one you like to transport sediment into the deep sea? This one or this one? I prefer this mode of transport. When you look at North American shelf edge, US Geological Survey have mapped all these mass transport deposits. This is published by the US Geological Survey. But there is no such mapping of modern turbidites. We spend so much time, but there is no map of turbidites in the modern deep sea. Why? Because they don't exist. And when it comes to the gravity flows, there are major types, 6 types. This I already talked about, hyperpycnic flows. We have turbidity currents, debris flow. These are all in the slope and the deep basin. And I have published this in an journal of the Indian Association of Sedimentologists. This is one of the most cited and read papers recently. And the last one in the previous classification is the thermohaline currents. That the example is in Antarctica, where the current actually comes down a sediment gravity flow and take a 90-degree turn, then move as a contour current. So I included the thermohaline current as a type of gravity flows. Now we go into deep water facies models. This is the late Arnold Balmer. He was the one who introduced the Balmer sequence. This is Professor Muti. He published papers on ancient submarine fan, facies associations, and so on. This is me 40 years ago. In the Balmer sequence, what he did was he recognized 5 divisions, A, B, C, D, E. Then he proposed, if you are in the A division, we are looking at the proximal part of a submarine fan. This is the map view. If you are in the E division, you are looking at the distal part of a submarine fan. So you can use this as a predictive model for depositional sediment bodies, reservoirs, deep water reservoirs. So this is very popular in the petroleum industry and even academic circles. In terms of turbidity current itself, there are a lot of experiments published. This is a turbidity current in a flume coming towards you. This is the map view forming like a submarine fan. When they deposit, they form normal grading. But these are all muddy sediment. They're not sands and gravels. When you go to Spain, you can see these beautiful turbidites forming sheet-like deposits. There are a lot of controversy about the Balmer sequence. So we started a field study at Mobile along with 2 of my colleagues, Roger Block and Dick Maiola. We went to the same area where Balmer studied his, that is Piracaba. This is the city of Nice. And I'll show you some other examples. This is the sections we measured and described and so on. This is one of the sections we studied. There are a lot of mass transport deposit, deformed beds, and so on. Balmer does not give much importance to this. He was more worried about these 5 divisions. And there are beds like this. He called it a turbidite. But when you look in detail, it shows inverse grading that you don't normally form in turbidites. You have pockets of large deposits of glass and other things. And you have a floating grains, floating plast. These are all typically occur in mass transport deposits, like debris flows, slumps, and so on. This is the armored mud ball. The whole thing got wiped out. I just put a yellow line to show the armored mud ball. And we have the large pockets of gravels. You can't deposit this by normal turbidity currents. It has to be mass transport. And we have double mud layers. You can't deposit this by turbidity currents. It has to be tidal currents. And you have sigmoidal bedding. Again, this is typical of tidal current deposits. We didn't know in those days when Balmer did this, he didn't know anything about deep water tidal currents. So you can't blame him. But at the same time, the model we use today is obsolete. So this is the model. Different people interpret it as differently. There is no theoretical basis for it. Nobody has experimentally reproduced all the 5 divisions. There is no observational basis. Like I showed you, we see all kind of different things. So we don't know what Balmer sequence is. So I would say we should abolish it. Then the other confusion comes from the use of the word turbidites. Scientists like Sanders, he would use the word turbidite for deposits of turbidity currents. This is what I follow Sanders. But Professor Muti and his colleagues, they say we can use the word turbidite broadly for deposits of any gravity flows like grind flow, debris flow, fluidized flows, and so on. So to him, the word turbidite means a general term, doesn't mean just the turbidity current deposits. So that's confusing to me. Then in terms of flow rheology, turbidity currents are the Newtonian fluids, debris flows are Bingham plastics. In terms of flow state, the turbidity currents are turbulent, debris flows are laminar. And therefore, Sanders said, if you see this kind of configuration, if you have a basal layer, laminar layer, flowing grain layer, he called it, it is not part of a turbidity current. Turbidity current is this upper part, okay? But there are papers, like papers by Postma and others, they did experiments. They lumped the upper turbidity current, lower laminar inertia flow, that is similar to the debris flow and so on. They called it high density turbidity current. I published a paper in the Journal of Sedimentary Research in 1996. The title of the article is High Density Turbidity Currents. Are they sandy debris flows? They did a survey from 96 to 2003, that is the International Association of Sedimentologists did. This was the most cited paper during that time period. So because of this confusion and complications about the density stratification in gravity flows, we funded a 2-year project at the University of Minnesota. We did some flume experiments. This is the flume we used. We introduced slurries. They come down the slope and they deposited, normally this type, a thin debris flow, thick turbidity current, more or less equal thickness of turbidity current debris flows, and a thick debris flow and a thin turbidity current. This is one of the actual photographs. This is the debris flow. This is the turbidity current. So these are the two distinct processes. You can't lump them together and call them high density turbidity currents. So there are two groups of scientists. One group, this one, they separate turbidity current from debris flows. There is another group, they lump all this into one and call it high density turbidity current. So this is another area of confusion. Now we deal with bottom currents. So far I talked about downslope gravity processes. This is along slope contour currents. They exist. And there are papers published by Talley and others that show the global circulation of these deep water masses and so on. I'll show one example near Mozambique. In the next picture, this is large ripples published by Heesen and Hollister that suggest there are bottom currents forming large ripples in the deep oceans. So there is a word called contourites that was introduced by Charles Hollister, and he said we should use the word contourites only for deposits of thermohaline-driven contour currents. But there are other authors like Lowell and Stowe. They wanted to broaden the term contourites to deposits all kinds like bottom current revert sands, tidalites, and so on. This is confusion. The next one is the internal waves. If you take any geology journals, or particularly petroleum geology journals, you'll see very few articles on this topic. The reason is it's complicated. So geologists generally stay away from anything complicated. So what I did is I have studied 51 examples of these internal waves all over the world, and I published it in the AAPG bulletin. And I'll show you two examples, one in the Pacific, one in the Andaman Sea. This is the Andaman Sea, the internal waves. This is the surface manifestation of what's going on underneath in the ocean. So this is what Gill studied. He said there is this surface wave called barotropic wave. When you go deep into the ocean, there's another wave called baroclinic wave. So this is so complicated, we stay away from it. In the paper I talked about in the APG bulletin, I found out, depending upon the depth of the shelf edge, the number of these internal waves vary. For example, if the shelf edge is at 50 to 90, 100 meters or so, you have 12% of the internal waves occur here. If the depth changes from 100 to 200 meters, then it jumps to 81%. Most of the internal waves occur at this depth. At deeper depths, it goes down. This is the horizon guyot in the Pacific. This is the undersea hill. The depth of the top of the hill is 1900 meters. You have the internal waves. They rework the sediment. And using this kind of data, I published this model in the AAPG bulletin. I suggested if you have the guyot, the internal waves rework the top of this area. And this has been documented by Lonsdale and others in their paper. They recognize large bed forms on the top of the guyot. And if you go to the South America, there's a paper published by Saint Laurent, and they said, these authors said, if you're dealing in the mid-oceanic ridge, internal waves occur here. If you go to the deep basin, they're absent. But there are very few geological journals that deal with this kind of thing. One of the rare papers published by some of the Chinese authors, Professor Gao, Professor He, they published papers. And there are some Spanish authors like Palmer and others. And I did my own publication. So these are very rare examples of internal wave publications. This is a huge area of future research. Then the loop current. In the Gulf of Mexico, the loop current comes in and gets out. I studied cores and so on in the Ewing Bank area. We have underwater photographs in the Gulf of Mexico at 3,000 meters water depth. You see these large ripples. Using all this, I published this paper in the AAPG bulletin in 1993, where you have the turbidity current coming down, the contour current, the bottom current goes this way, and they intersect, forming the hybrid flows. When I published, people ignored it. People thought I was crazy. And more recently, people are paying attention to this model. There's a paper published by Fonasu and others. They proposed this similar model for the Mozambique, where the gravity flows coming down the channel and the contour current going this way, very similar to the one I proposed in 1993. And this is another area of future research. Then submarine canyons. They occur all over the world. This is the North Sea, North Atlantic, the cluster of submarine canyons published by Twitchell and Roberts. This is on the west coast, near Los Angeles, submarine canyons. Again on the west coast, Mississippi Canyon. When you plot the cross-section of the canyons, this is published by Normark and Carlson. This is the world's largest canyon, Chemsheng Canyon. You can literally plot the La Jolla Canyon near San Diego. It's a little thing. So canyons occur in all shapes and sizes. And they took core. This is published by Paul and others. These are mainly debris flows. And they took underwater photographs of debris flows moving down canyons. But there are no photographs of turbidity currents moving down canyons. They have sand falls. And in 1979, Shepard and his colleagues published this data saying that in the submarine canyons, we have tidal currents moving up and down to a depth of 4,000 meters. These are very deep water, but very few geologists use this model to interpret the ancient. There are few papers, but not many. I used this for the canyon in Nigeria, the Edo field, where we have a canyon. I showed from the core a lot of slumps and debris flows. I also showed what is called double mud layers. What this means is because the currents going up and down, they tend to form couplets. This is very unique to the tidal currents. That's why I put this question mark here. But there are very few documented cases. Mine is a very rare case. Then we go to India. This is called Krishna Godavari Basin. I consulted with Reliance companies, and this is one of the amplitude map. But if you don't have core or log or things like that, you can look at this part of the map. You can say there's a channel coming down. There's a large lobe forming. You can say this is a submarine fan composed of turbidites. But because we have core and seismic, we can tell exactly what it is. This is the bathymetric image showing that core well 2. This is the canyon. When you look at the core, we have large clast floating in sand. These are sandy debris flows. When you look at, you have a lot of double mud layers. These are tidal currents. So when you put seismic into the core, this is the shape of the canyon. This is the core plotted. Using that, we published this model. This is the canyon. This is the core. I published this along with the Reliance colleagues like Sanjay Srivastava, Bhagwan Das in Journal of Sedimentary Research. It's a very large paper. You can go and refer to it. Then the turbidite groupthink. This is 22 authors led by Pope and others. They published this paper in the Butte Inlet, that's in British Columbia. This is the study area. These are the studies done by others. They documented the tidal range of all these things all over the place. The tidal range, 4 meters, 5 meters, and so on. But these authors ignored this tidal information, and they came up with a model. All the deposits they studied are turbidites. They ignored other possibilities. This is a good example of a groupthink. Ignore obvious data and go with the preconceived notion. So this is another area of future research. Then another area of groupthink is sequence stratigraphy. In the 90s, 80s, so on, Vail and others, they published models for deep water deposition, sequence stratigraphic model. I'll show you what it is. You can look at the seismic geometry. If you have mounded geometry with bidirectional downlap, they call it basin floor fans. That means you are dealing with turbidites, clean sand, sheet sands, and so on. So using this model, companies in Europe, they drilled wells into these mounds in the North Sea. They came up with the mud slumps instead of sandy turbidites. So the government, UK government, wanted to know what's going on here, why there is a problem. So we did a 5-year study in Mobile. We were 15 scientists. We looked at the core and seismic from the North Sea and so on, 50 wells. We described 12,000 feet of core. I described all of them with my colleagues for 5 years, and we published this in the AAPG bulletin. I'll show you that one example, the North Atlantic, the Faro Basin. This is the seismic, mounted geometry, bidirectional downlap. This is the core we have. Theoretically, this is a basin floor fan. Therefore, you should see a lot of turbidites. When you look at the core, you have just a jumbled up mess. I'll just show 2 close-up photographs of this core. Slumped beds, but it is below seismic resolution. You can't see it in seismic. And sand injection, you can't see this in seismic. Revert sands, you can't see this in seismic. So in this particular area, you have slumps and debris flow constitute 92%, and the bottom current revert 8%, and 0% turbidites. What happened to the model? So the UK Department of Trade and Industry, there are a lot of people worried about this kind of findings. So they contacted me and they said I should organize a deep water workshop for people in Europe and other places. So I did in 1995, 97. People from Europe, America, Africa came and watched, examined the core and seismic. They could not believe what they see in the core. So you should always look at the core if you really want to understand what the depositional origin of these reservoirs are. The next is tsunamis. This is the Lituya Bay in 1958. It's a 524-meter high tsunami. If you put that in Chicago, this is the Willis Tower. It used to be called Sears Tower. It will topple the TV antenna tower. So huge. And in 2004, we had the Indian Ocean tsunami that generated from here, and it went all the way to India, Ceylon, Somalia, and so on. That's my hometown. It was affected by this tsunami. It killed 227,000 people. So because of all that, I was interested. I did a review paper on tsunami published in the Journal of Sedimentary Research in 2006. This is the model coming from that paper. So you generate earthquakes and it causes tsunami waves, hit the shore, and cause erosion and deposition of large boulders, and return and deposit in the deep sea. This is one of the examples of the boulders left behind by the tsunami in Pacific. It's published by Froelich and others. I gathered examples of tsunami deposits all over the world, published a paper in the year 2012 in a special issue of Natural Hazards edited by Arun Kumar. And in that, I showed the various types of tsunami deposits. Can be cross-bedded, can be laminated. There is no unique sedimentary structure that you can say this is caused by tsunami. Can be any one of these. So this is another one of those areas of future research. Then sediment deformation. I have been studying sediment deformation since 1965 when I was a student at IIT Bombay, where they have monsoon rains, a lot of landslides, and so on. These are the examples of study localities I have studied over the years. What is a soft sediment deformation structure? There is a unique deformed bed sandwiched between undeformed beds. That's what SSDS means. This is I published in the Journal of Paleogeography. This is an unhydrated bed, deformed in between undeformed beds. And they occur in all basins, but there is a general tendency to call these SSDS as deposits of earthquakes. They call it seismites. This is misleading because seismite means you have to have evidence for earthquakes, like this one. This is a paper by Alsop and Marco. They did a study in the Dead Sea Basin where they can document these deformation is caused by earthquakes. So you can apply the term seismites. But when you have this many options, when you have a deformed bed, unless you can demonstrate that it was indeed documented by earthquake, you cannot call it simply as a seismite. You have to establish what the triggering mechanism is. It could be a meteorite impact, a volcanic activity, glacial loading, salt tectonics, and so on. So this is another area of future research. Then I reviewed the Oppenheimer movie. It was directed by Christopher Nolan. This has nothing to do with deep water deposition. It's something I did. The reason I did is because he started out, he is the father of the atomic bomb, and he started out as a geologist. And then he moved to chemistry, and then finally into physics. What he did was he studied Bhagavad Gita. In order to study Bhagavad Gita in the original language, he learned Sanskrit, one of the difficult languages. So you can imagine what a brilliant person this Oppenheimer was. Anyway, they developed under his guidance the atomic bomb. They dropped it in Hiroshima and Nagasaki. As a result, the World War II ended. The consequence is today we have a Russia-Ukraine war going on and a Israel-Gaza war going on. They're talking about using nuclear weapons. So this is the consequence of nuclear weapons. But Oppenheimer always was against using nuclear weapons. But the US government thought he was a bad person, and they punished him, taking his security clearance and so on. They mistreated him. But President Kennedy recognized something great wrong was done to him. So he invited 49 Nobel laureates to dinner at the White House. He also invited Oppenheimer to dinner there. But Oppenheimer is not a Nobel Prize winner, but Kennedy wanted to honor him. So things like that done to him in order to restore credibility. I wrote a very long review, right about his life in a chronological manner, some of the scientific contribution he did, and so on. The next movie I reviewed is called Far from the Madding Crowd. This was written by Thomas Hardy in the 1800s. This was the leading lady actress is Julie Christie, one of the best British actresses you can think of. She was born in India. And the reason I was interested in the movie is it was set in the 1800s. The southern part of the southwest England where the story is set, it's composed of Cretaceous chalk. All right. Why I was interested? Because if you plot that Cretaceous chalk that falls here, if you plot the CO2 through the ages, today's CO2 is 420 parts per million. It's about 2,000. It occurs during a peak period of CO2. To me, that's important geologically and to understand the climate. Coming back to the movie, these are the cliffs that's in the movie, you can see. And the lesson from the movie is noble deeds are rewarded. If you do good things, you'll be rewarded. If you do bad things, you'll be punished. The next thing is climate change. I was introduced to climate change by Professor George De Vries Klein in 1988. That's the year the UN started the IPCC, that is the Intergovernmental Panel on Climate Change. And he passed away in 2018. So we dedicated a special issue of the Journal of the Indian Association of Sedimentologists. We have papers on climate change by Gerrit van der Lingen, and I wrote a paper on his life, and I extended life of George Klein. I published a paper in this, so on. I'm also a member of a group called CO2 Coalition. This is a nonprofit organization co-founded by Professor Will Happer. He's a professor emeritus physics at Princeton University. He was also born in Tamil Nadu, India. The goal of this organization is to provide facts, resources, information about the vital role of CO2, because there are a lot of misinformation saying CO2 is bad for planets and so on. So we want to set the story right. There's another movie I reviewed. It's called The Climate, the movie. It was released earlier this year. The importance of this movie is they interviewed 17 world-renowned scientists, and including a Nobel laureate. And they concluded, using data, the climate scare going on today is a scam. just to make money. Some people are making money out of this. So let's look at the energy itself. Sun is the primary source of energy, whether it is coal, natural gas, solar, wind, hydro, and so on. I published this in a recent issue of the IA's magazine. You can find out in the June issue, actually. So if you take a barrel of US oil, it's converted into 46% gasoline that you put into your car, 9% jet fuel that goes into the plane you are flying with, and 26% diesel and so on that we use in various areas. So without oil, you cannot survive. You cannot lead your life. And they're talking about reducing CO2 to save the planet. Let's see how that works. Germany emits about 2% of CO2 into the atmosphere, and India 6%, China 26%. Let's say Germany is able to manage to get to 0%, say 0% CO2 from here. It doesn't mean anything because so long as these countries emit CO2, the atmosphere is an open system. There is no wall here separating atmosphere above Germany from atmosphere above India or China. So the whole thing is just bogus. Then we go to the next item. They say if you reduce the CO2 along with the atmosphere, we can save the planet. Let's see how that works. Because of the greenhouse gases and CO2, we have a comfortable temperature of 15 degrees centigrade in the atmosphere. So if you remove this atmosphere, along with CO2 and so on, we will go to this temperature, minus 18 degrees centigrade. That means we all will die. So when you reduce the CO2, we will save the planet, but we will kill the people. Let's see what happens when you reach net zero. That can be reached only if you abolish all petroleum products, 100%. Otherwise, you cannot reach net zero. Let's see what we'll do on a one-day experience. You go to the bathroom in the morning. There won't be a toilet because it's made of petroleum. You want to brush your teeth. There won't be a paste. It's petroleum product. You want to jog. There won't be a jogging shoe. So you have to, because this is petroleum, you have to jog without a shoe. There won't be a car, plane, ship, cell phone, mask, or pillow. So without this, you have to live on a net zero condition. How do you do that? There is a way. You have to move back to the caves and live like Neanderthals. They didn't have cell phone, car, or mask, and so on. Now let's go to the science itself. They say if you increase the CO2, that will increase the temperature. Let's take the classical sign. This is the Rayleigh-Jones curve. That is, the energy comes continuously. This is the Max Planck curve. Here, the energy comes in discrete packets. So we can use this to calculate how the CO2 controlled temperature and so on. This is what Van Wijngaarden and Happer did. And this is the Will Happer I mentioned earlier about the CO2 coalition. What they did, they took the Max Planck curve and they said, we are going to double the CO2, say from 400 parts per million to 800 parts per million. So intuitively, you would think it's going to increase the temperature tremendously. But they found out the increase in temperature is minuscule, irrelevant, less than 1 degree centigrade. So when they published, a lot of people, the global warming crowd, got very uncomfortable with this scientific fact. Using all this information, I published a paper in the Journal of Geological Society of India last year. What I did was I plotted the various data for the year 1900, 2023, and the year 2100. So let's take today, the temperature is 14.51 degrees centigrade. IPCC predicts in the year 2100, it'll go to 16 degrees centigrade. This is all wrong. I can tell you how it is wrong. All you have to do, if you are listening to this talk in Beijing, for example, you go out and measure the temperature today, right now, you'll see it'll be in the range of 30 degrees centigrade or 35 degrees centigrade and so on. This is literally double the amount of the predicted temperature for the year 2100. So the people who are listening to this talk, they're not dead. So the whole thing is kind of scaring people. But if you were in a classroom, you normally have a CO2 up to 2,000 parts per million. You are flying, it has CO2 at a range of 5,000 parts per million. So we do this everyday basis. We are not dead. So the conclusion is there is no climate crisis. There is no emergency. There is no catastrophe. There is no existential threat. Just leave the planet and people alone. We'll be fine. Then the peer review problem. We get the manuscripts, the author name is removed, so it's blind, meaning that you are going to do your objective review of the paper and so on. But you can easily figure out who the author is. All you have to do is look at the references section. Usually the author cites his paper or her paper. So if you see 5 or 6 publications by the author X is the author. So this is all, I think, a waste of time. We should abolish the blind peer review process. I have published a paper on this some time ago in the Journal of the Indian Association of Sedimentologists. My hobby is photography. Wherever I go to the various parts of the world, I take pictures, unique pictures, and publish on the cover of journals. This is the pulpit rock in Norway, published on the AAPG Bulletin. If you watch the movie Mission Impossible Fallout the last time, this is where Tom Cruise is fighting the bad guy exactly in this area. This is the tower cast from China. This is the turbidites from Spain. If you watch the TV series Game of Thrones, this is where the Dragon Queen walking around during the last season, you may remember. So this is a very famous rock. And this is the volcano in Ecuador. This is India. This is again in Spain. This is Ganges River in India. This is halide crystals on contourites. I have published 8 journal covers in Indian journals. Now we have reached the end point. That is, how to improve the impact factor of the journal Energy GEOSCIENCE. Let's take these 3 journals. The first one is AAPG Bulletin. It was founded 170 years ago. It has the impact factor of 3.5. Journal of Paleogeography, founded 12 years ago. It has an impact factor of 2.5. Energy Geoscience, it's a baby, just 4 years ago. Impact factor is 1. How we can improve this 1 to 2.5, say during the next 10 years or so. That's our goal. So we can use Journal of Paleogeography as a guide, as a role model. The reason I do that because I've been working with Journal of Paleogeography during the last 10 years. And during the last 10 years, I have published these review articles for the journal. They are of different domains: landslides, submarine fans, seismites, breccias, turbidites, and so on. Early on, Professor Feng and I decided review articles are the ones that attract new readers. So we did this. In all these articles, I try to be original. I do not follow groupthink. So that's me. As a result, there are a lot of people try to read my papers. We have data from the ResearchGate stats. I just took this 2 days ago, July 28th. Number of reads, 207,000. That's a lot of reads. Citations, 9,200. If you go to the Google Scholar, the citation is 12,323. The most cited article is the 50 Years of Turbidite Paradigm I published in the Marine and Petroleum Geology. This is where I discussed the experiments on sandy debris flows. I talked about density stratification, high density turbidity currents, and so on. That's that paper. The next most cited paper is the significance of coniferous rainforests and related organic matter. I talked about resin and kauri trees in New Zealand, oil coming from leaves and so on. So when you do the very fundamental research, address the fundamental problems, people read these papers. To take an individual article, this is published in the Journal of Paleogeography on landslide, that this paper alone reached 11,000 reads. That's a lot. Anyway, because of this, the journal gave me an award. And recently, the China National Knowledge Infrastructure gave me a certificate because the submarine fan paper reached the top 1% of the most cited papers during the last 10 years. The reason Journal of Paleogeography has done so wonderfully is because of the editor-in-chief, Zheng Zhaofeng. And he and I did great works together. Some of the things he did that improved the journal, the very first one is he appointed some of the brilliant editors in the headquarters, like Dr. Yuan Wang, Dr. Zhu Fanghu, Dr. Min Liu. He appointed international editors like Professor Somerville, Professor Santanu Banerjee, Professor Xiaobin He, Professor Stephen Hersha. He encouraged me to publish review articles. He published a lot of discussions, editorials. He founded the International Society of Paleogeography. So that's the real reason the Journal of Paleogeography is thriving very well with 2.5 impact factor. These are some of the editors who helped me during my tenure with, this is Dr. Yuan Wang. She has been the one I have been working with most with the journal since 2014. She was the first person I contacted in order to publish a discussion in the journal. There are also a lot of Indian scientists who helped me. These are the 10 people I recognize: Professor Ghulam Bhatt, Professor Nayak, Santanu Banerjee, the same one who served on the JOP, Bashir, Armstrong, Professor Ram Kumar, Shokan, Chandrasekharan, Sarbani. She passed away 2 years ago. She was like my sister, one of the most important and brilliant sedimentologists. We miss her. And of course, Dr. Will Happer. He was born in India, although he's a professor today at Princeton. So this is my conclusion slide. Words of wisdom. I have only one word. All you have to do, remember the word China. The word C stands for critical thinking, comprehensive analysis, clarity in writing, CO2 focused, common sense applications, deal with Chinese energy. And the letter H stands for humanitarian, I stands for insightful, inspiring, innovative, N for neoteric, and A for articulate. So that's my words of wisdom for the energy geoscience in order to improve the impact factor. If you can apply these factors in selecting the article that you are going to publish, there is a very good chance you can improve the impact factor. So I want to thank Xuanjiang Sun. She is the deputy editor of Energy Geoscience. She invited me to give this talk. Dr. Yuan Wang was participating in this endeavor, and all these oil companies, Professor TNM, Professor Feng, Zhai Jian, Qing Bao Zhang.
Okay, thank you, Professor. Thank you for this brilliant lecture for us. And so we have, how many times do you recommend for the Q&A session, Professor?
How much time?
Yeah.
As long as I live.
Because it's already 10 o'clock at night in Houston, so
How
I don't
about
know.
15 minutes?
Okay. 15 minutes, right? Okay.
15, 1-5.
OK，所以我们有15分钟的时间，然后提问，大家有没有什么问题？ And also our former vice president and the editor-in-chief of Energy Geoscience Journal, Feng Zhiqiang, is with us online.
Oh, okay.
Okay.
Hello, Professor Shanmugam. It's a very nice talk.
Thank you. Shiji.
Yeah. So I'm in Hangzhou now, not in the main, not in Beijing.
何院长，你有什么问题要跟
我现在还没有。
？OK，看一下，我把我的摄像头打开。Okay, Professor.
Yes.
I have a question.
Yes.
You talk about the different perspectives of from engineer and geologist from the very beginning of your lecture. You put out the concept of deep water.
Yes.
And there is various opinions, in the mind of engineer and geologist. And my question is, as a geologist, how can we, how can we convey our opinions of the geology, marine petroleum geology opinions to the engineers in order to support their work?
Oh, okay. Very good. When you talk to an engineer, explain to him that geologists are more interested in the deposition origin of the rock, that is the reservoir.
Yeah.
We are not too much concerned about the construction engineering problems when you build a platform and things like that engineers are worried about. So long as you can explain to them, geology is about rocks, not about building platforms. And our interest is to understand how the rock was deposited in deep water or shallow water or some other environment. Then they will appreciate that. Am I making it clear?
Yeah, yes. Thank you. And then I have another question.
Sure, go ahead.
Your work spans a wide range of topics, including, the conventional petroleum geology and also the nuclear weapon and the carbon dioxide, the climate change. And how can you integrate all these kind of works?
With the great difficulty.
Mm.
Well, the reason I do climate change is, as I said, in 1988, I got involved with Professor George Klein. I'll tell you the story. In 1988, I submitted a paper on submarine fans to the Earth Science Reviews. That is the major journal at the time, even now. And George Klein, Professor George DeVries Klein, was the editor-in-chief of that journal in 1988. So when he received my paper was along with one Dr. Richard Mayola. It was a Shanmugam Mayola paper. It's called Submarine Fans Characteristics, Models, and so on. It's a very comprehensive work. And he liked the paper and he published it. Ever since, he and I become like friends. He was almost like my mentor. He was the one who started sending me all the articles on climate change. And that was the year 1988. The IPCC was founded. So ever since I was paying attention to climate change, I tried to integrate, for example, I was talking about a movie called Far from the Madding Crowd, where the movie is set in southwest England, where the rock is Cretaceous. It's a Cretaceous chalk, although the movie is about the lady in the movie, but my interest is about the Cretaceous chalk. When you plot that on the curve I showed you, the carbon dioxide curve, through geologic time, you can find Cretaceous was a high number of CO2 during the past, about 2,000 parts per million. That's how I integrate what I learned from climate change, from the geology of the area. So we can combine climate change to geology. That was a very good example. And I also like watching movies. So when you combine movie, geology, and climate, you can integrate. But there are not too many people who like to do that.
Okay, thank you, Professor. And Dr. Yuan wants to ask you two questions.
Hello, Professor Shan.
Yes?
I want to first make a comment. Comment one. I like the cartoon photos in your lecture. The one about people will get back to a cave life if all the petroleum will be abolished. Yeah, this is the first one. And also the last one, also the last slide, your explanation for China. So yeah, yeah. That's the most two photos for this lecture. I want to make this comment. I have two questions. The first one is about soft sediment deformation structure.
Yes.
Because yes, because we both in GOP and also other journals, international journals, for example, sedimentology, we have a lot of publications on this topic. So my question is, how do you suggest or recommend to, let me say, some critical criteria for the outcrop observations for identifying the let's say maybe some quick identification, a criteria for identifying the triggers for the soft sediment deformation structures, which I mean just full field observations.
Yes, yes,
So
yes.
that's my first question.
Okay, let me answer that first question.
Okay.
Actually, when I wrote the paper, the seismite problem for Journal of Paleogeography, you remember that Professor Feng liked that paper. He and Min Liu translated into Chinese. Do you remember that?
Yes, yes.
It was published in Chinese. The reason for that is in that paper, I gave a lot of examples over the years. I studied in the North Sea and other areas where I have very good geological background to say they were triggered by sediment loading, not earthquakes. So that's how you go area by area. For example, in the Gulf of Mexico, there is an area where the Chicxulub meteorite impact took place. If you look at sediments in the adjacent areas, you can say those deformations were caused by meteorite impacts, things like that. So you have to go area by area to recognize what was the triggering mechanism that caused the sediment deformation. For example, in the Gulf of Mexico, there's a lot of salt tectonics going on in the slope. So there you can suggest that salt tectonics is the triggering mechanism for the soft sediment deformation and so on. And then, for example, in the Sumatra area, there was the 2004 Indian Ocean tsunami, earthquakes, and so on. So this is, you got to go area by area and try to eliminate some of the other possibilities, trying to narrow down the most likely possibility.
Yes, I ask this question because due to the on a field trip, post-conference field trip of actually the second ICP, we had this field trip in Shandong province. We saw a lot of this SSDS on the island, and also we, I mean, all the attendees, we talked a lot, discussed a lot about the triggers, mechanisms of this outcrop. So yes, I agreed with your opinion on at this lecture. Actually, a multi just based on the observation of the outcrops should incorporate a lot of other let's say evidence from drilling wells, yes, lithology like this, yeah. So that's also
regional geology is an important aspect of it.
Yeah, it's important. So that's also led to my second question. Because you are you are distinguished. You have a lot of distinguished experiences in deep water, and you also had some distinguished experiences in establishing models for such researches. Actually, I have handled one paper submitted to GOP about last week, which challenged a model about a typical Trinity, let's see, a Trinity model for a foreland basin. So that's the challenging from the author of this paper. So my question is, according to your experiences and knowledge, what would you recommend for young scientists to, if it's appropriate to just to establish such a model, and after, because possibly after the subsequent studies, it will be possibly be challenged or it will be accepted by subsequent studies. So what would you suggest to about establishing such a geological model?
It actually depends on for example, when I started, I was not particularly, I didn't think I'll be going into various areas like I have been, like in dealing with seismites, dealing with coal beds and things like that. One thing I have learned over the years is the more broader knowledge you have, the better understanding of the thing you are doing locally. In other
Yes.
words, if you focus on one thing all your life, you may miss out on some important points. So the broader knowledge is, to me, is vital. That's number one. Number two, try to avoid trying to follow the popular models. There are a lot of journals and articles that try to follow popular models so that they can get accepted and published and so on. I think they should go with the data. If the data suggests even unpopular things, then they should accept the data more than the popularity of a model or something. That's the way I would go for young scientists. Stick with the data. Don't worry about the popularity and unpopularity of a model and so on.
Yes, sure. Thank you.
You are welcome.
专家有没有问题 Okay. Thank you, Professor. And then we will wrap up for your lecture. And thank you very much and good night.
Good night, Zizi.